Physics students, good afternoon. Mr. Fugit here. In this video, we're going to be looking at some applications of the Work-Energy Theorem, which we've been covering the past couple of weeks in class. So this problem specifically is geared to address problem number 11 on your homework over work and energy. Problem reads as this. A 12-gram bullet is accelerated in a rifle barrel 61.6 centimeters long to a speed of 731 meters per second. Use the Work-Energy Theorem to find the average force exerted on the bullet while it is being accelerated. So here, we're told we're to use the Work-Energy Theorem to find a force value. So what I'm going to do is I'm going to go ahead and write out both of our equations we use to find work. Force, displacement, cosine of the angle between them, and work is equal to a change in energy. Now in this problem, we're told that we're firing a bullet. Okay? And initially, that should trigger in our minds that we're going from a bullet being at rest to a bullet moving. So we're changing that bullet's, approximately its kinetic energy, if you will. Now, as long as we're firing, let's say, at a level height, for the most part, which we're not told specifically here, but we can kind of assume that in this scenario. Okay? What's happening is that as we apply that force over a certain displacement, okay, it's going to cause our kinetic energy to go up. We're adding something in to the bullet, right? So what we're going to do is in the problem we're told to find a force value. Okay? We're given a distance here, a length of the barrel that we'll probably use for our displacement, kind of how far the force is being applied over. We'll talk a little bit about the angle here in just a moment. But in order for us to find this force, we need to first find the work that's being done. And here, the work that's being done, we're going to say, is specifically going to go to change the kinetic energy of our bullet. Say, as it's moving along that barrel, its vertical height, if we're just shooting it at kind of level point, the vertical height of our bullet really isn't going to change much. Primarily, the energy that's going to change here is our kinetic energy. So we'll say here, the work being done is equal to a change in kinetic energy. So if the bullet is at rest, beginning in the barrel, that means it doesn't have any kinetic energy. And then when it exits the barrel, we're told we're at a very high velocity. My value is 731 meters per second. So the final kinetic energy we have, minus initial 0, we're really looking for what's the final kinetic energy that we have. So we'll say the work done is equal to our kinetic energy, 1/2 mv squared. So work done is 1/2 times the mass of our bullet, which, be careful, is given to us in grams. So 12 grams, 0.012 kilograms, times our velocity, 731 meters per second, squared. Now let's take a moment and plug that in. 731 squared times 0.012 divided by 2. That's going to give us a value for the amount of work being done. And I get right at about 3,206.2 joules. Okay? That's the amount of work that's being done on the bullets. How much the bullet's energy is increasing, right? It's gaining some kinetic energy here. Now, that's not what the problem is asking us. The problem is asking us, what's the average force being exerted on the bullet while it's being accelerated? Okay? Really, how much force is being exerted on the bullet to get it to do this, right? To get it to gain this amount of energy. Okay? So now we're going to use our other approach for work. So I'm going to take this value, 3,206 joules, and now we're going to use it in our other approach for, got a little blurry there, my apologies, and we're going to use it in our other approach for work to find a force. So here, work is equal to, you all know how the board can be. Here, work is equal to force, displacement, cosine of the angle between them. Okay? So I'm going to take a second and recalibrate the board just to make sure that we see these numbers and they actually show up nice and clear. Yeah. So we're going to use the length of the barrel as our displacement, the delta x, and of how far the force is being applied over, but we also need the angle between those. Okay? So let's kind of write this out, see what we have. Up here, work is equal to force times displacement, cosine of the angle between them. Now, we're going to get our bullet let's say, moving a certain direction. Kind of our gun is going to fire the bullet out to the right. Okay? Now, in order to get that bullet moving a certain direction, some force has to push it there. Let's say it's just a force from the, it's really kind of a combustion reaction in the gun, but it's just going to cause a force to move the bullet. So we have a force pushing on our bullet, and the bullet's also going to move that same direction, right? And we've talked about this scenario before. If the force and the displacement are in the same direction, well, there's no angle between them. So cosine of 0, no angle, will just give us 1. So it simplifies down what we're doing here. Now we're just going to set this up just to solve for the force. Okay, so here's what let's do. We just calculated our work done. 3,206.2 joules is equal to a force that we don't know times the distance, delta x, over which our force is applied. And we're told, let's say that force is applied all throughout the barrel. The length of the barrel is 61.6 centimeters. So be careful, we need to make sure we convert that. 0.616 meters. Now, once we've set it up in this way, we'll notice it's really a matter of just trying to get force F by itself. So to do that, we need to divide our delta x, 0.616 meters, on both sides of our equation. 0.616 meters, divided on the right-hand side, which will get that value to cancel out, and 0.616 meters on the left-hand side. So if we plug this in, we'll take 3,206.2 divided by 0.616. That gives me a force value, F, equivalent to 5,204.8. We're measuring a force here, so our unit should be newtons. Okay, let's check our key, see what we get. 5,204.8. We're right on. So here, rather than us solving for the work or the energy, here we're solving for the work and then kind of backtracking that to find the amount of force being applied on our object to change its energy. So we're still using that same relationship of work and energy that we've been learning about, but here the application is just a little bit different. So hopefully this gets you started better on working problem number 11. Best of luck.